Hey, in this video, we're going to learn all about gravity. And as we learned in a previous lesson, we know that gravity is a non-contact force, and it's an attractive force between two masses. Now, when it comes to what the cause of gravity is, there are actually a few different theories on this, or a few different perspectives on what's causing gravity. The classical perspective is field theory. And gravity as a field was just that early attempt, classically speaking, so we're going back just a couple hundred years, and gravity expressed as a field was just an early attempt at describing action at a distance forces. Scientists didn't understand how two objects could interact with each other and exert forces on each other whenever they weren't touching, because virtually every other force is a contact force, with the exception of electric forces and magnetic forces. And so they developed the idea of fields to explain how you can exert a force without making contact. So a field can be most generally defined as you're going to have some variable, and in the case of gravity, we would use the letter G, and G would be defined as the force of gravity divided by mass. And this basic model here is what we're going to use for all the different types of fields that we're going to look at. Now, I don't want you to do anything with this right now. We'll explain fields in much more detail here in a few minutes. But that's basically the field theory. It's just that somehow this massive object is able to reach out into space, and when you place another massive object in that space around it, then you end up with a force being exerted. The second perspective that we can look at when it comes to what is causing gravity, it's a bit more modern, and that would be Einstein's theory on gravity, which is a curvature of space. And of course, Einstein is the one that's famous for this. Now, the curvature of space is really describing the field. Okay, so you've got this field. We don't know what's really going on. We just know that this mass puts some type of stress on the space around it. And when you place an object in that stressed space, then the object feels a force. Well, Einstein said that space is bent. And there is a lot of evidence which we have today that says very definitively that space does get bent near massive objects. It's, in fact, the idea of space warping and bending is one of the reasons that we know that dark matter even exists. And dark matter, of course, is dark, meaning that we can't see it. It's not that it doesn't shine light, it's that it doesn't interact with anything that we can see. So Einstein's theory on gravity actually kind of embellishes field theory. All right, and then the third perspective, which is purely theoretical, uses a particle called a graviton. And the graviton is a shared particle between the two masses. Now, this might seem kind of strange that we're talking about a shared particle, a graviton, being shared between two masses, and that somehow creates a force. But here's the thing, it's not unfounded. And for example, electromagnetic forces, they're going to use the photon. Okay, so electromagnetic forces share a photon, and the electromagnetic force is the most common force. And, that's anything from friction to why you feel something when you place your hand on the desk, or you grip the steering wheel of a car, or pedal your bicycle. What makes paint stick to the wall. Those are all electromagnetic forces, and it's the result of a photon which is being shared. Another example where we know very definitively that there is this particle would be subatomic structure. So the gluon The gluon is shared between quarks. And quarks are what make up protons and neutrons. And so whenever they do their experiments with these particle accelerators, they see evidence of these gluons. So the idea of having a particle which is shared is not unfounded. However, the graviton has never been observed directly and probably never will be observed directly. And I'm not going to get into the reasons for that, but you can look it up on the internet. That information is quite readily available. So our focus is going to be really on number one, and that is that, we just have this gravitational field which exists in space, and that gravitational field is defined mathematically in a very simple way that we can work with. Now, the force of gravity can most generally be defined by the equation Fg is equal to g m1 times m2 over r squared. Okay, and this is known as Newton's universal law of gravitation. But we're not going to look at this as a law the way we've defined laws in class. It's a law in the sense that it will accurately predict the size of a force between two interacting bodies to create this gravitational force. But in terms of larger contexts, it doesn't apply as a law. Remember, we've defined a law as being able to explain interactions where we use Newton's second law in order to get like accelerations, for example. We're going to treat the universal law of gravitation as a definition and not as a law itself. Now, this is going to be in our classic theory of gravity. This is going to be the most general expression. And what I mean by that is this. If you're doing a problem which involves gravity, you can always use this equation, provided, of course, you know what the two masses are that you're working with. And that's not always going to be the case. But this is the most general, and that's also why it's called the universal law, because it applies everywhere in the universe with the exception of black holes, for example, or when you get down onto the atomic level, because once you get to that size, really, really small, then you end up having issues with quantum mechanics and the effects of quantum mechanics getting involved. And so the law begins to break down at that point. But for virtually anything that we would ever have to work with, the universal law of gravitation works just fine in all of the situations. All right, so let's define a few of these things here, these variables. So we have the force of gravity. That's going to be measured in newtons. So it's got units of newtons. G, this is the gravitational constant, and that's 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. M1 and M2 are the interacting masses, and the masses are going to be measured in kilograms. And then R is going to be the distance between the masses. So, for example, you might have mass 1 right here and mass 2 right there. And R is the distance between them. Okay, and notice I didn't draw this so that it was on just the x-axis or just the y-axis. And that's one of the reasons we use the variable r, because it's more like polar coordinates. It's literally just the distance. So when it comes to deciding for the vector nature of gravity, is it going to be a positive force or a negative force, that's going to depend on your coordinate system. So for example, mass 1, we have the force of mass 2 on mass 1 would point up and to the right, and then equal and opposite to that, we have the force of mass 1 acting on mass 2. Both of these are the gravitational force, But if you wanted to work a problem involving these two masses, we might be able to just leave it so that our coordinate system is parallel to this to these vectors. But if we had to use an XY coordinate system, then you can have the force in the Y dimension and then the force in the X dimension. So we'll deal with this a lot more through examples and in class. So this should become more clear if it's not clear just yet. Now, the other thing about R is that this distance between the masses, this is going to go from center of mass to center of mass. This is only going to be valid for point particles or spherical shaped objects. So we'll add that note as well. And the spheres themselves have to be uniform with their density. It can't be a lumpy mass distribution throughout the sphere. Let's take a look at a simple example of using the universal law of gravitation. Okay, a typical problem that you might see in an introductory physics book might go something along the lines of Sally sees Johnny on a dance floor 10 meters away and feels an attraction. If the attraction is due to gravity, how large is the force? And then we're going to assume that both Sally and Johnny have the same mass, and this is all just to keep things very simple and straightforward. So the first thing you're going to do is draw a picture of the situation, and we've got two people, and we're just going to represent them with with these circles or spheres. We're going to represent them as point particles. And so we're going to have Sally over here on the left, and we'll put Johnny over here on the right. And the distance from center to center is going to be 10 meters. And our job now is simply to calculate the force of gravity between these two people. So first thing we need to do is decide which person we want to calculate the force of gravity for. And our problem says we want to know what force Sally feels, because Sally's the one that feels attracted. Now that doesn't mean Johnny doesn't feel any kind of attraction, because he does, right? Because it takes two objects to create a force, and both objects are going to feel an equal and opposite force, and this is due to Newton's third law. Right? Newton's third law explains that. It's always going to take two, and both objects are going to feel the same force, just in opposite directions. So for Sally, to draw our FBD here, we're just going to have the force of gravity, which is pointing to the right. If it were Johnny, then the force of gravity, it's an attractive force towards Sally, that would be pointing towards the left. But this force and this force are identical, described by this equation. Fg is equal to g m1 m2 over r squared. And we can use 1 for Sally and 2 for Johnny, or vice versa. Or we could say g times ms mj over r squared. Okay, so you can see that calculating the force is straightforward here. G is 6.67 times 10 to the minus 11. Sally has a mass of 60. Johnny has a mass of 60. And the distance between them is 10 meters, and so we'll square that. All right, so what's going to happen is this is going to become 10 squared is 100. So we can cancel this with these two zeros here, because 60 times 60 is going to be 3,600. All right, and so let's go ahead and calculate this. All right, so we have 6.67 EE minus 11 times 60 times 60 divided by 100. And that's going to give us 2.4 times 10 to the minus 9. So that's 2.4 times 10 to the minus 9 newtons. or 2.4 nanonewtons. So this is an extremely small force that is there, and this is not a force that they are capable of feeling. Our bodies just can't register a force of that size. Okay, now remember before that we talked about the force of gravity and weight. And weight, we said, was the attractive force between an extremely massive object and a much smaller object. The force of gravity is going to be any attractive force between two masses. And so basically what we're saying here is this: all weight is a force due to gravity, but not all forces of gravity are we going to call weight. Just be careful to make that distinction. In the cases where we're talking about weight as this attractive force between a really massive object and a much smaller object, in those cases we tend to use this equation. The force of gravity is equal to m times g. Now, the reason I even brought up the difference between these two terms is because, at least in my classroom, we never write weight is equal to mg. We don't do this, okay? You may, if you're not one of my students, but we don't use W for weight. We use Fg for weight, okay? And it's because all weight is a force due to gravity, but not all forces due to gravity do we call weight. So we end up with Fg is equal to mg. Now, this equation here is what we would call the near-Earth approximation. You may also hear it called the flat Earth approximation. And all it simply says is this: if you have a flat Earth that extends way out into infinity, if we have an infinitely wide plane, then whether you're located right here or somewhere really far away, the force of gravity that you experience, that attractive force for you and this infinite plane, is always going to be the same. It's not going to change. This is not something we're going to really explain in any great detail in this course. Mathematically, we're definitely not going to show how to do that. But if you take AP Physics C, then you'll get a much better understanding as to why this statement holds true. That no matter how far away you are from an infinitely large plane, then no matter how far away you are, that force of attraction is always going to be the same. The reason we go from flat Earth to near-Earth approximation is because the Earth, being so massive and so large that whenever you're standing on its surface, if you ignore all the hills and the valleys, it appears to be flat. And it would appear that the force of gravity is constant no matter where you are. This use of gravity, this term, this near-Earth approximation, this is only going to be valid whenever we're, I'll say, plus minus 4 miles of the Earth's surface. So basically, anywhere in the biosphere would be valid. It'd be fair game for using Fg is equal to mg. But when you start getting outside of those limits, the approximation starts to fail us, okay? But it doesn't fail us at a very fast rate. But this is why we use Fg is equal to mg when we're near the surface of the Earth. Now let's look at some details related to this. Okay, so Fg equals mg, that comes from universal gravitation. Fg is equal to g mass 1 mass 2 over r squared. So what we're going to do to help get to this is we're going to look at this equation. You can see that all of this stuff here appears to be the letter G. Okay, so, and it is. So G is called the gravitational field. And you learned in kinematics that it was the acceleration due to gravity. G near the surface of the Earth is going to take on a value of 9.8 newtons per kilogram. The acceleration due to gravity was 9.8 meters per second squared. And so anytime you see the letter G, it's always going to have the value of 9.8. In kinematics, we get G is equal to 9.8 meters per second squared, and that's going to be downward. And then in forces, we write G is equal to 9.8 newtons per kilogram, and they're both going to be downwards. Okay, so the direction is always going to be the same. And this is perhaps something that maybe you really haven't thought about yet, but I know as a student it was something that I thought about, and it took a long time for me to resolve the differences. Because you see, in kinematics, when you're solving a problem, you just use G is equal to 9.8, you put the numbers into the equation, and out comes the right answer. When we're doing problems with forces and we have to use gravity, you throw the number 9.8 into your problem and you come out with the right answer. So what's the difference? What gives between these two values? Why are we distinguishing between 9.8 meters per second squared and 9.8 newtons per kilogram? Now, not to add any kind of insult to injury on all this, but the fact that we write both of these using the letter G, and they both have the same value of 9.8, then they should both actually have the same fundamental units of meters per second squared. So if we do a unit analysis of the newtons per kilogram, we get a newton is going to be equal to a kilogram meter per second squared, and that's going to be divided by just kilograms. And so kilograms cancels out, leaving us only with the units of meters per second squared. So does that mean that 9.8 newtons per kilogram is the same thing as 9.8 meters per second squared? Especially when you consider that the mathematics of it is always going to work out the same because they both have the same value. The answer to that is a resounding no. On a practical level, we treat them as the same. But in reality, they represent two totally different things. You see, with kinematics, we're all about motion. And in kinematics, acceleration is defined by a change in velocity over a change in time. And so when you consider the equation Fg is equal to mg, and you say, well, it's just mass times the acceleration due to gravity, conceptually you're incorrect. Mathematically you're correct, but conceptually you're incorrect. And physics is all about being precise conceptually and mathematically, but if you don't do the math, you still have to be precise conceptually. So the reason you're conceptually incorrect, and this is the part that I struggled with as a student. So you write, mass times 9.8 meters per second squared because you decide you don't want to make the distinction between the acceleration due to gravity and the gravitational field. But here's the problem. If you want to figure out what your weight is as you're sitting in your chair right now, you take your mass, you multiply it by 9.8, and you get your weight. And the number is actually correct. But you're not moving. And that is a big problem because by definition, acceleration requires a change in velocity. And in kinematics, when you're accelerating, you are having a change in velocity. Yet when we're talking about forces, you don't have that change in velocity. So in forces, we refer to it as the gravitational field, and that is a totally different concept. The gravitational field is basically the way a mass can reach out into its environment and exert its presence. I mean, I guess that's the best way to put it. So it's you'll have a force when another mass comes into the field, but you won't have a force until that time. So the field is just a way a massive object can interact with its environment when it has nothing to interact with, no other mass to interact with. Now, as soon as you place a mass there, you have a force according to Newton's third law. It always takes two objects to create a force, and we no longer just write G, but we actually write Fg. So basically, the gravitational field is the force which will exist. Well, I can't say it's the force that will exist, but it's the potential for a force to exist if you place another mass in that region. But if you don't place another mass in that region, then it's not possible for the force to exist. So the big idea conceptually is that the acceleration due to gravity, as given in kinematics, requires that you have that change in velocity. When it comes to forces, you're not required to have a change in velocity. All it means when you have a gravitational field is that a massive object is nearby, and that if you place another mass in that field, in that region of space that's near the object, that test object, whatever it happens to be later on, is going to feel a force. And how much force does it feel? In the case of being near the Earth, it's going to be 9.8 newtons per kilogram. So if you look at your equation, if you have a 10 kilogram object and we estimate G to be 10, then we end up with a force of 100 newtons. And if it's a 2 kilogram object, we end up with a force of approximately 20 newtons. Okay, so conceptually that's the differences between these two. This G leads to acceleration, this G leads to force.